Hi, everyone. I'm Ian Trase. I'm a machine learning engineer at Flagship Pioneering. I'm excited to tell you all about how Flagship's using AI in partnership with Activeloop to enable bigger scientific leaps. So we're really excited about what we've built together and how it's improving the workflows of our researchers. I want to basically go through a brief introduction about what Flagship is, what our group, Pioneering Intelligence within Flagship, does, and then sort of the source of the problem, what we did to solve it, how we tested it, and finally, where we think it's going to go in the future. So Flagship Pioneering is sort of like a venture capital firm, but instead of going out and finding companies to invest in, they start their own. And so the whole idea behind this is to sort of understand and use the science of company foundation, especially in the biotech space. And so we've been doing this for almost 25 years now. Over 100 companies have been founded, 30 have gone public, which is a pretty good ratio. The biggest company that most people have probably heard of from Flagship is Moderna, but we have several others and many more in the pipeline. So at this point, we're quite large scale, and so we do quite a bit of research in order to basically say, all right, what companies, what new ideas are out here? How can we combine existing ideas in interesting ways? What ideas are people not looking at that they should be? And so all of this is powered by a group of a couple hundred associates at Flagship. And these are generally almost all people with PhDs in biology who've worked in multiple different fields. And in general, it requires lots and lots of literature search. So every day they're reading multiple papers, they're looking up lots of information. It's a very knowledge-heavy field. And so within Flagship a few years ago, the leadership noticed that most of the companies that they were starting were using AI or machine learning in some form. This is probably not surprising to all of you guys, but almost every new biotech company that comes out is using machine learning for things like protein generation or target detection, all that sort of stuff. And so Pioneering Intelligence was founded to basically be a center for knowledge, a way to push the fundamental limits of what exists in the biological machine learning space, both in terms of molecular models and in terms of mining scientific literature. And so our work has, over the past few years, spanned many domains. We've got molecular design, DNA design, language models, reinforcement learning. We are very sort of technique agnostic. We see a problem and we say, all right, this is a biological problem. How do we solve it? And over the course of this, we've been working with Activeloop for a while now. We started working with them looking at effectively data loading for very large-scale biological data to train protein models. We then moved on to saying, okay, well, we have these language models now. We'd like to use them for scientific knowledge retrieval. And that has since moved on to things with hybrid search, agentic workflows, all that good stuff. So the challenge is effectively, how can we enable this sort of innovation at scale? As I said before, this involves reading a lot of papers. And specifically, our associates are often not reading papers for their sort of main thesis, the headline title. We're asked things like, I want to find all the papers that use this particular method, and I want to draw conclusions based on that. Or something else that isn't really very upfront in the paper. And that is the sort of thing that traditional search can fail at. So as we saw in earlier talks, like general BM25 sort of keyword-based search will often focus on the wrong things. And so when you have something that's not top line, it becomes very difficult to search for. Another good example of this is you'll often have biological things like proteins that have like multiple different names and multiple different papers. And we want to be able to not have to search for 5 different things. We'd like to be able to correlate it all automatically. And so now onto the solution. So we basically said, all right, well, Google Scholar and tools like that are not working for us. And this was about a year ago. So why don't we take what open source data we have, pull it together, and create a vector database that basically has all of scientific literature. And that would basically be a database that we can build off of, that we can make multiple sort of internal tools that could accelerate our sort of research pipeline. And so I'm going to spend a bit of time on this slide, but I think it's probably reasonably familiar to most people who have built RAG applications. We start with a database, a sort of a database called OpenAlex. I think you've seen Activeloop has also been playing around with it. It's basically a database that has all of the titles and abstracts for almost every scientific paper, including things like metadata, citations, all that stuff. And it aggregates from a lot of the smaller things like Crossref and PubMed. And so it was a good starting point. We then embed that all, and I'll go into a little bit of how we chose which embeddings to use. That's all put into a deep lake database. Then on the user side, a user can submit a prompt. There's an execution agent. That agent takes the prompt and transforms it into one or multiple search queries. And this is a technique that we found really boosts the quality of the output as opposed to directly embedding the user prompt. It just tends to give better results. And then obviously we basically got a cosine similarity search. We apply filters. We pull some relevant context that's then put into the prompt, and you get your answer. So very similar to how a lot of things are done today. And yeah, so this was a collaboration. Activeloop was focused on the database and optimizing the embeddings, whereas we focused on the front end and basically figuring out how do we make this agent framework to boost our recall and give high quality answers to our researchers. So for a lot of these text-based applications, testing can be non-trivial. As an example, the way we decided to test is there's a database called sentences that is effectively a bunch of sentences that are either pulled or indirectly pulled from a paper. So they're basically facts, right? That have a single paper that says, oh, this is where that fact came from. And so that was basically, we said, all right, well, if we take that sentence, and we either embed it or transform and embed it, and then pull our papers, ideally, we'd like to see that paper that the sentence came from be returned. And so when we started working with Deep Lake, we saw that it was doing significantly better than sort of traditional vector search, but you're still only seeing about 50% recall. And I focus on recall 10, which is if we pull 10, is it within the first 10 papers that we pull effectively? Because that at the time was about where we were, like how many papers we were putting into the context of the final agent. Now we probably care more about recall at 100 because context lengths are significantly longer. And so we wanted to dive in, like, why were we only getting 50%? So the major reason was data set size. So again, this is not super surprising based on how actual like vector stores work. As you increase the number of items in your vector store, the chance, if you're at a certain point in the vector space, the chance that there's something else very close to you goes up. And so we saw this very strongly as we rose from only 2,000 papers to 40 million, which is all of PubMed, a sample subset of OpenAlex. It dropped from something like, 88% to 50%. And so that's something that can be solved or at least ameliorated with things like filtering, and fuse search and all those other techniques, which are techniques that we now use. The other thing we noticed is that as I went back, the recall metric was not perfect. So originally we were looking for exact matches, right? But if you really think about how papers work, it's very unlikely that a single scientific fact is found in only one paper. It's often found in many papers. It can be found in that paper and all the papers that cite that paper, or all the papers that are cited, that paper cited. And so we moved to a different metric for evaluating quality. Instead of basically saying, okay, we need an exact match, we took all of the results that were given by the retrieval system and passed them through an LLM and had the LLM basically say, is the sentence found in this paper? And once we did that, we found that the results were much, much better. And so again, we see that the important number is in the heat map is down in the lower left corner. If we return 10 samples, at least one of them is a good result 93% of the time. And at least one is what we care about, because that's all it takes for the LLM, which is a high precision system, to pull it out. And this number was before we had things like fuse search and filtering. So it's probably closer, frankly, to 99% now. So that's basically how the sort of retrieval side of things worked. I also want to talk a little bit about how our agentic workflow worked. In the beginning, it was very simple. So we basically just set up a pipeline that took in a user query, turned it into a search, returned value, returned documents, and generated a final answer. And this was okay, but we were exposing it in a chat interface to make it easy for people to use. Then we found that people were often using it in ways that we didn't anticipate. So people would do things like try and ask follow-up questions, which it didn't understand. People would ask questions that were not at all related to literature and didn't need a literature search and get very weird responses. So we ended up trying to go in a little bit of a different direction and have a more free-flowing system. So we basically said, all right, a user gives a query, decide what it is. Is it something that needs a literature search? Is it just a normal question? Is it a follow-up question to a search you already did, in which case you effectively want to reuse the documents you already grabbed? And so once we incorporated that, we found that the results became much better, and usage additionally also became much better. And so that's effectively how the system works now. We're really excited about where this system is going to go in the future. I think we've set a good base for all of Flagship to be able to effectively use this deep lake system. And I know there's several projects beyond what we've already put out in terms of our literature search tool that plan to use this in a more industrial scale way for automatically searching and extracting information and going back and searching for more information, so on and so forth. We're also very excited to start incorporating full text data where we can. OpenAlex right now is mostly just abstracts, but we think that adding things like full text and images found in papers will be a huge unlock. And we're also trying to move to, we've built all of this agentic stuff ourselves, but we're starting to consider moving to other advanced agent systems. Paper QA is a good example of them that do this sort of deep, much deeper search where they will go and they will search and they will read the papers they retrieve and they will search again and again and really dive very deeply into the literature. And so we're very excited about where this is going to go in the future. Yeah. So thanks for the attention.